Thank you again for attending this event. And we are planning to do this kind of webinar monthly basis in the second half of 2023. So please keep your interest on the Midas expert webinar series. Yeah, and then I will pass the mic to today's speaker, Arash Behnia.
Thanks, Adam.
Please.
Good afternoon, everyone. Good afternoon, everyone, and welcome to today's webinar, where we want to discuss fundamentals of integral, basically fully integral and semi-integral bridges, and along which there are some tips in the process of designing of integral bridges based on, I assume most of our attendees from Australia, so we are focusing on Australian standards and some guidelines and some tips in the Midas modeling. Quick background about myself. My educational background is primarily civil and structural engineering, from my undergrad degree to master, and my PhD focus was on bridge structural head monitoring. Well, I kicked off my career as an engineer starting on various infrastructure projects, especially power plants projects, power plant station projects for a few years. And after that couple of years, I for very short times, working on a high-rise project. And in 2014, I started working on infrastructure, focusing on tunnels and bridges, mainly on bridges, and range from construction engineering and permanent work design, and also proof engineering across different countries, like from in Asia Pacific mainly, and some project in Europe, a couple of projects in Europe, and there are types of project I was involved in the past few years. So I jump to the next, and currently I am in infrastructure team with Robert Group, and our company is associated with the Urban Drone, basically as a parent company. We have presence in Australia, Europe, Asia, and USA, and we have two main expertise, which basically Robert Group was established on was building, and then another expertise which is the infrastructures and construction engineering. I myself in the infrastructure engineering and construction engineering team based on Melbourne. Well, I would like to first give you a quick rundown on the presentation objective. Then the following contents, basically you can see here the introduction of integral bridges. After that, we want to just touch base on the early design phase methodology, how we plan, how we do a concept design for any type of bridge, in fact, and introduction to our project, which is focusing on Northeast Link package, one of the packages projects, and then why we are choosing integral bridges, and showing some of 1 or 2 pages of drawing, the PD drawings. After that, we just go and check how we do a modeling in Midas, and then what part of system to be modeled. And after that, some load cases, main load combinations, which are very important, and moving loads. And finally, some tips in the design and things you have to be careful when using any softwares. And yep, and we'll be, if we have time, we do basically pick up some question if there is any question. I would like first to basically clarify what's the objective of today's presentation webinar, which is topics we want to cover is fundamental of understanding of different types of integral bridges, mainly in Australia, and then design requirements for integral bridges and available options for modeling in Midas software, how we can model that basically, and modeling tips to what you have to consider, and touch base on the construction methodology and the modeling factors in Midas, and overall analysis design option. But what we don't want to cover is basically there are many tutorials available in YouTube's or in the Midas webpage. You can really go and get understanding of how step-by-step modeling. Here we want to focus on basically, we want to focus on and what the topics are not really clearly defined in the tutorials, and we can have a discussion what factors you really need to consider when you design the integral bridges or using Midas. So from here, I start basically the introduction to the bridges, integral bridges. In fact, integral bridges are pretty popular in the USA, and they have been around for quite a while. It has gotten to the point, well, several DOTs in the USA come up with their own design guides, standards, and codes. And the reason why integral bridges, and in fact they call it integral abutment bridges, are so popular in the USA is mainly because of harsh environment in USA, and they show exceptional durability performance, and we will talk about that in depth why they have great performance in terms of durability. And since they have been using this, the reason is that they have expansion. They don't have any expansion joints, which is creating a great opportunity for durability performance, and they tend to hold up very well over time. But anyway, in fact, in Australia, the climate condition is relatively mild. Everyone knows that. So that's why they bridge authorities and bridge owners haven't felt the need to develop a unique guidelines for integral bridges and integral abutment bridges in the same way as USA DOTs have done. But however, after recent application, there are several applications, not several, but it started to pick up the number of integral bridges in Australia. So it started to gain popularity among the bridge owners and also engineering community, especially bridge engineering community. And it's not surprising, to be honest. Why? Because it's not only a performance in terms of durability. So it's like they require, if you are using a fully integral bridge, we are going to talk about that. They have a minimum requirement for maintenance, and it's really huge costs in maintenance period. And then if we don't have bearing for fully integral bridges, it costs saving there. And also we have the construction methodology is quite, if you use, it's pretty efficient, and it's not expensive to build, unless, like, if we talk about fully integral bridges, there are some difficulty. We can touch base later on. But if you use the semi-integral bridges, they are really easy to build, and contractors love that. And you do not need much flexural capacity, and that is another thing. And it's like, this is very good because you can use a simple super T, or you can use a plank to design a quite quick design process, and also efficient design with minimum requirement flexural capacity. And you basically do not worry about the precision requirement in the construction and during installation of bearings. That is another point. So mainly we have two types of integral bridges. Excuse me. The first type is, as you can see here, full integral bridges, and we have semi-integral bridges. So full integral bridges, you can see in this figure. In fact, you get the full fixity. We need to achieve a full fixity between the superstructure and the abutments. And to do that, you need to form the fixity by ensuring the deck and beams, superstructure, are cast integrally with the abutment, which is a substructure. So they have to be cast together, and always, not at the same time. You can have basically different methodology to basically build, but always the beam need to have the reinforcement to be put to that from their ends to the abutment, and then to basically to deck reinforcement shall be turned down to the abutment. That is a must for full integral bridges. Then you can create a full diaphragm, and you can basically create 100% moment connection. And you can see here in the right figure. So it's the reinforcement is basically turned down. While in semi-integral bridges, you do not basically need to do that. And then this is more practical, and contractors love it because of ease of construction. The typical Australian practice for basically a small size, medium size to shorter span. We are talking about 15 to 30 meter spans. Although codes in Victorian standards, they are allowed to go to 60 meter for concrete or 70 meter, but I have seen like 30 meters, like is a practical length. And so you don't basically shorter span bridges, and then you can eliminate the need of expansion joint. And to do that, you can see here this called link slab. So you adopt a link slab over piers, and while you're still having the bearing, and you should have a debonding layer. Probably is not very visible here, but you can see debonding layer to create discontinuity between the girder and the link slab. So the link slab still cover expansion joint. There won't be an expansion joint, so it's great for durability. But because this link slab itself doesn't have huge rigidity, so you do not transfer bending moment together, and that will help basically to have minimum bending moments and very simple structure and at the pier. So basically, what I also want to touch base on that is that's important to note. When we talk about integral bridges, the choice between integral and semi-integral is it varies, but I would go personally with the semi-integral bridges in case if there is no requirement, a specific requirement. So the main reason is that when you don't have full integral bridge, you don't have bending moments, and you have basically you have a determined structure. So it's not indeterminate structure. So isostatic structures are basically independent from soil structure interaction, and also you don't have differential settlement impact on your structure, and then thermal movement, and which I touch base in depth later on. And then, but on the other hand, you don't have bearing in full integral bridges, but then you will have less bending moment at the middle span, but then you have bigger moments at pier. So in short, if we do not really require a huge bending moment demand at the middle span, the best is to go with semi-integral bridges. So for integral bridges, in fact, so I just highlighted here the main points. So I will just go through it for everyone to get the understanding of that. As I said, semi-integral bridges is preferable because of ease of construction, and isostructure structures, there is no secondary effect from creep and shrinkage. In fact, creep and shrinkage are very critical for fully integral bridges, even more than conventional, because there is no joint to accommodate any movements. And in fact, the shrinkage and creep, which they have two phases, primary and secondary, which we talk about that in Midas modeling, they have to be considered in the design methods, and they are really important factors. It can change whole analysis result. So if you have a semi-integral bridge, you really have a better situation in terms of the creep and shrinkage. And as I said, no significant bending demands in the span. Go with the semi-integral bridges, much easier in construction as well. In fact, the linkage span transfer the bending moment, as I said, that is a requirement. You have to make sure there is a debonding layer. That debonding layer is critical to avoid any cracking in your top fibers. And basically, in both cases, regardless of semi-integral or integral fully integral bridges, the horizontal forces from the substructure basically are transferred or transmitted to abutment by diaphragm action. So we will see here in this project, we did not really need to have a diaphragm because we will see later on it's a 20 meter span, and then diaphragm could be created at the ends, and you simply don't need to have like a super tier structure creating diaphragm in the middle of the girders. You can see the diaphragm can be created at the ends if you're using a simple plank pre-stressed beams. We'll talk about that later. And yeah, as I explained, provision for thermal movement should be made basically out of, so there is no expansion joints. And as you can see here in this figure, for the movement joints, for thermal movement joints, the acceptable practice in Australia, basically in Victoria, is to have the joints out of the deck. So it's like after approach slab, between approach slab and road slab. So basically that's the location which usually can have movement joints. This is a requirement based on some guidelines. 70 meters is the maximum you can go for concrete for. But if I have 70 meters, basically, usually I won't go with the plank. Of course, we go with different type of gathers. We can go with the Mega T or the SPGs, but we are not talking about that in this webinar. So, and it is very important. In no cases you don't have a huge thermal cycling movements between two if you are using full integral bridges, which means this 20 mm maximum minus and 20 is given in the guidelines, but it's not a must as long as you can accommodate. But this is like this is a limit for you to have in your design assumptions, because due to the cyclic movements, you will get different passive and active pressure from the soil, and then this is induced from the thermal cyclic displacements, and then that's in. So if you don't have it, you really have less stresses on your piles, and then the piling will be a huge issue if you have that cyclic forces, and then you will have a huge piles, and then also even abutments reinforcement. And it is advised basically a straight bridge is easy and a small skew is like 10 or maximum 30 degrees to avoid any basically rotating in the plan due to the thermal induced actions. That is also advised to avoid if you have a degree more than 30 skew degrees. So you should basically go with the other options rather than fully integral bridges. Definitely go with semi-integral bridges if you need to do so. And that will help you to reduce the forces in your abutment because of the thermal cyclic force. So, in summary, when we do a design, when we want to do a bridge in bridge conceptual design, there are factors to pick about the solution. So if you don't have like usually when you do a tender in the tender phase, clients ask you like, come up with 2-3 solutions before going to the premier design. So you usually come up, if it's a small project, you do a reference 2-3 options. If it's a big project, probably you do a reference design. So to do in the conceptual design, usually you look at the roads, and then it's like, what is the skew degrees and geometry of the roads and the environments, what's the climate condition there, and also it's very important, the soil profile, soil specification. So the soil profile is one of the key factors. If you have a very different soil profiles in 2 different locations, and left and right abutment, south and north abutment, you really get the big issues with potential differential settlements from left to right, from the north to south abutments. So you don't want that. Then you should really avoid full integral bridges. And going with the indeterminate structure is the best option there. And also the bridge span, as we touched base stats, and also the project delivery time, the construction in terms of construction time, and then material, and also site constraints. Sometimes you don't have mobilization. What's the traffic there? You need a road closure, or it's like what's the maximum span you can close? All of those factors, and then also construction sequencing. You will see in this project now. We had 2 different construction sequencing, and that's one of the reasons we decided to go with the full integral bridge, and also cost. And eventually, sometimes you don't have any option, like you will have only one option, and then you go with that option. So a quick introduction to the project. Basically, now we talk about, we had discussed, basically I touched base on the factors on the design phase. So here is like Northeast Link project, which is one of the, basically the biggest Victoria, Melbourne, Rogers infrastructure project. And then this project basically is going to deliver twin roads tunnels in Melbourne dedicated for bus. There's a first dedicated busway as well. is going to be 34 kilometers walking and cycling paths over 16 suburbs. Rothenberg groups have been and are still going on project undertaking of design two intersections, basically interchanges, underground interchanges, D-walls, under cut and cover D-walls, and ramps, which are at Lower Plenty Road interchange and Manningham roads. You can see some of our ongoing phase of design, which has been completed, and then basically in the next year we finish CPS phase as well. So the longest cut and cover tunnel for us was 350 meters long and 50 meters wide and 30 meters deep precast vaults. So in one of these interchanges, which is Manningham Road, you see in the next slide here, I will explain. In Manningham Roads, we have basically cut and cover, and over cut and cover walls, we should have created a bridge in the Bridge Street. And we will talk about that. Then the reason, basically, here I'm going to discuss what was the reason we basically decided to go with full integral bridges, and why not we didn't go with semi-integral bridges. And in fact, it's like, first is like we checked the degrees. We have like probably 15 to 16 degree of angles, skew angles, and the span perfectly fits for integral bridges, 20 meters span. And we have a cut and cover D-wall, which has a huge stiffness and create a proper support bedding and abutments for superstructure, and that can easily transfer bending moments, and which means we are not worried about the forces on. We didn't need to worry about the forces at each side of advancement, so we could basically reduce the depth of the beam. And also we were required, because there is a road at two side abutments, and then we needed to keep the finish level of the bridge in a certain road level. So we have no option to keep that level, and we couldn't change the depth of the beam. So definitely we want to minimize the bending moments, demand bending moments at Midas span. And also there are requirements, because that was in the project brief, it was designed, so requested to be designed for the earthquake design class 4. And as you know, is the class 4 is we need to do a dynamic analysis, and also to do that you have also you need to consider the ductility between superstructure and basically a P delta effects to substructures of walls. So there's another reason for the full integral bridge concept. And also the clients didn't want, this is tunnel you don't have access to, it's not easy access for changing the bearing as well. And clients also didn't want to have any expansion joints for maintenance reason. And then clients just simply wanted to have the full integral simple solution and no bearing. So that are all the reason together came to the point we decided, and of course that's the best option for us to go full integral bridge rather than semi-integral bridge. You can see in the next slide, that's basically that's the bridge we are talking about, and it is in the Manningham Bridge Street intersection, and it has 30 meters width, which we had 10 lanes, if I'm not mistaken, 10 lanes. And so there are, in the plan, we have some skew angles. In the vertical angles, we have some angles as well. And this is basically a cut and cover walls. And that is approach slab. We designed the approach slab based on requirements, and also the joints happen after approach slab, as discussed earlier. And we use a solution. Basically, this is the solution we adopted for. This is a standard plank. Probably most of you are familiar with that. That is a typical, usually in Australia, it's very popular to use super tiers for a longer, like a 30-35 meter span, or like 40 meter max. I think for 34-35 meters max for super T, if you want to go with a standard T1 to T4. And if you have a sections which is like the lengths, which is 15, 12 to 18, 20, 19 meter, if I'm not mistaken, these planks, pre-stress plank, are super handy. So you basically have a shear stress tendons, they're top and bottoms, and then they're typical. And you can simply design it, and then also you can decide on the debonding. What is the debondings? Like here we use the typical, we use the 20, there are 20 strands which we added 2 extra strands we needed 2 extra strands and top strands for negative bending moment, and also we needed to create debondings to make sure we don't exceed the compressive and stress tension forces in each stage in the construction staging. And you can see here basically details of planks. We have planks 600 by 600. The maximum height, this is 600 in height, 600 in width. This is a box. The largest, I think, is 700 in the height and 600 in width for 19 meters span. And you can see here the reinforcement we created to make sure that, as explained earlier, the rail turned down to abutments to create full rigidity. And that was to ensure all the ductility and all stress development length will be achieved. The plank are placed the construction stage first, and after that, basically, you can see there are shear bars, and then the concrete slab will be placed on top of that in the second or third phase. That's in this also image, you can see that the plank and then the concrete, and at the ends, as I explained earlier, we didn't need to have any diaphragm here. To be honest, that's very simple because you have all the planks next to each other. So diaphragm, as you know, creates a lateral stability, and more important factor from diaphragm is that you get a proper, even vertical load distribution between all your girders. So diaphragm has a very important role in the bridge design, integral bridge, and any bridge. So here we had basically filled in growth with the growth at the end of the span each side to make sure everything is like fully restrained laterally and also create a proper diaphragm. So for Midas modeling, so now I'm gonna highlight the main items in Midas modelings which we used and you can use in your Midas modeling. So the best, really, I'm very happy with using Wizard. Usually I use it if I want to do a super straightforward solution, or doing a reference design, or doing a concept design. It's very easy, fast, everything is ready. In an hour you have your bridge model ready for 1 or 2 span, even 3 span, and then you can tweak it if you want, and that's a good thing you can use. But if the structure is very complex and you need to change everything, then maybe it's not worth it, and you can go basically start modeling from scratch, which is going to be time consuming, but of course there's less errors, you have everything under control. And so I'm not going to go in details talking about how to model that. There are tons of tutorial available, but I'm just talking about what options we can have. And option 3 is basically import. This is my favorite one when I have like a design proper complicated geometry. And another one is basically a trick is import in 2 steps, like what I did for this project. We had in another software an initial in the concept design. In the detailed design, we really needed to do more sophisticated analysis, and that's why we basically exported to CAD, from the CADs imported to Midas. And then when you do that, there are few things you have to check, is like joint and nodes overlaps, and also making sure there is no item overlapping, which in my case it didn't happen in this project. And also setting groups, which we talk about that in details, because very, very important factors for construction staging. You need to create a setting before doing anything. When you import your model, first you start working on creating groups, on structure, on the elements. And basically, and what the question is that if we have the bridge model in another software, why we used Midas, right? It's like, so to me, it's very simple. Different software, they are giving you eventually should give you the same result. But we had a very specific case, and it was very interesting and challenging, not interesting in the time of design. So the client was not sure what's the construction methodology. Is it top down or bottom top? So that can change the whole design scenario. So that's why it's a very user friendly in terms of having your your construction stage in Midas. That is one of the, I think, the most strongest point of the Midas application is the construction stage to me. And you can basically define your construction stages and tweak it, change it, and then you can have different scenarios. And basically, you can create two different scenarios, top and bottom, in different stages. And also, the another point is that I knew we have the Planck geometry ready. That is the geometry defined, and you just need to tweak the and do a debonding definition or optimize your debonding. So that's the reason we did Midas, and modeling this was important. And so when we want to model, basically, regardless which software, and we have basically a couple of options. Usually we use a plate models or beam models, but as simple as possible is the most important things to everyone, probably. And then we have to be objective oriented, what we want to achieve. So in my case, I had in this case, we had two stages of modeling. One is like first preliminary design, and in that case, superstructure and substructure. Superstructure was together. The best solution usually is grillage model. I think is a very familiar solution for everyone. A simple 2D model structure which has a linear elastic behavior. And then you can see here in this image, you design, this is your beam and this is your slab. So you define a longitudinal elements, these elements as basically a beam. You define the size as a line elements. And then as a transfer, and then your slab, rather than being a plate, will be transferred, will be defined as a transverse member. So basically you have a slab with 250, you can define like 500 beams with a 250 depth and then each 1 meter. So that creates basically, eventually with the longitudinal and transverse direction, you will have a beam, a composite beam. So a beam members, which is laid out in the girded patterns. And when you want to extract the result, you can get your result for each composite section. The reason we do that, because the load distribution is going to be very realistic. And also, another thing is that when you want to get your result, you don't need to go search for the plates and then separate it. And also, when you want to apply the loading is going to be very easy, especially the moving loads. So the point is that when you do that way, basically you will get a composite action, and then in your result and design phase, you will design the composite section, and you don't need to separate beam from slab. That is really, really good way of doing a bridge modeling if it's possible. For substructure, basically for D-wall, for the cut and cover walls, we had this D-wall you can see here, and we have basically a capping beam on top of the D-walls, and we have supporting a slab you can see here, and we have a temporary heavy-duty shorings during the D-wall installation. So what we define is basically first round of analysis, we define as a beam element everything, because we wanted to get the feel of what's the depth of the beams I need, and then what's just the general understanding. And then it saves you a lot in terms of computational time when you design, when you want to run a plate element. Of course, that's going to be very expensive in terms of computational cost. So, but in the final stage, we didn't, because in the first stage, we didn't really worry about the D-walls itself, but then in the final stage, to see everything together, we model as a plate element, the D-walls. And of course, everyone knows that the meshing is very important to make sure the nodes and mesh are defined properly between the D-wall and the girder. And on top of that, the capping beam we define as a beam. And then here the D-wall supporting a slab. In any case, we didn't really we didn't look at the result for that. So we just wanted to create lateral support and to create that rigidity. We just create the beam elements, so to avoid huge computational cost. So, and as you can see here, so in the first, after defining your groups, we will go talk about that next slide. It's very important. That's the main topic I want to talk about. After defining your basically the construction stage, you go and define your groups, and then you define your material. You can see that's the ready items there. You just need to import your concrete properties here, and then you can go and define your creep and shrinkage. If you are going to use, like, let's say section 610, if I'm mistaken, Australian Victorian guide, you can You can modify the creep and shrinkage here, but then when you define your creep and shrink concrete properties, you need to activate your time dependent. That's sometimes people define time dependent, but they don't activate that. It is very important to activate that time and link it to your material. So otherwise, it doesn't function. So you need to activate and link it to your material. And this is basically, we use the predefined Australian standard, easy, from AS 1500.5. And then for load consideration, basically we have, you can see I have 27 load cases, and we need basically to define static loads, moving loads, wind loads, seismic loads. And then we had like type of loading, we have temporary loads, we have basically permanent loads, we have dead loads, and we have live loads. Like for example, temporary loading is about concrete, wet concrete, which is just happening in construction staging, and you have to remove it after that. And construction staging also is is the most important things basically in the bridge modeling. And to design basically seismic loading, to have that, we basically use EDC, I think ECD, design class 4, and it's a dynamic response. So you have to convert all of your mass, basically a portion of your live loads or even no live loads, and then your self-weight plus any mass superimpose, permanent superimpose. And you just simply go and just convert the loads to the mass. And then you have your parameters for soil category and ground acceleration and response spectrum factor based on AS 1500. You choose based on the project data, and you add your load case for the response spectrum. Construction staging, basically there are few topics you should be very careful about the construction staging. Is first stage definition. For stage definition, you can just go to loads, and in load you can define the CS, which is defined construction stage. And in each stage you have 3 parameters we can see here. Like you have to define which elements, which boundary condition, and which load. They are the most important things in the modeling. Again, I'm going to emphasize that. So then we need to define, on top of that, you need to define composite section. This is also very important. Sometimes it's being missed and being defined incorrectly, and you get the totally wrong result. This is a very important factors. So for example, you have your beam in a stage 2, and then you have to define your section start to be composite in a stage 3, and define the edge here. And then you make sure all of these factors are linked to your composite section. So I think this is not something complicated, but should be carefully defined. This is very important to be defined properly. And then the edge factor here, software can calculate for you. This is the creep and shrinkage thermal factors. The software calculate for you, which is in AS. You can find it is based on the perimeter length of the section. So in this case, we had 4 construction stage. D-wall, basically, again, we have 2 scenarios, top down and bottom. So I'm talking about the bottom to top. Imagining this in this presentation, we have the D-wall, basically temporary, and then temporary supports, and then a slab, and then you bring your girders. And then when the girders is resting on the D-wall, this is basically a stage where you have simply supported connection. Then the concrete will place the stage, next stage. You have the concrete, wet concrete. This load of concrete goes to the girder. So you need to define that load to be taken by girder. And after like next stage, you have to change the boundary condition to make it fix. It means now the bridge acting as a composite section. So we will see here next slide. Basically, as I explains, let's say here we have basically, this should be defined when you define your construction stage groups. You can see here the groups you need to define, like group for loading, group for boundary condition, and group for members. Whatever you define in your group will be appeared here. So then, for example, you choose your elements and you start basically to activate and deactivate. Let's say here in the stage 2, the wet concrete was activated, and in the stage 3, the wet concrete deactivated, which means the force will be taken as a composite action because the structure act as a composite action. Also, when you define, that was a bit challenging again. So when we define, let's say for the construction stage, we have to define when the soil is Ka, active pressure, not pressure, and P, passive pressure. Let's say you have the structure here without any support, without any lateral support. After placing that, your structure is subject to K active. But when you place your support and you place your girder, the structure to have to K active should be removed as a boundary, as a load, and transferred to K not, which is K. Basically, there is no active pressure anymore because you have already supported at the top of your D wall or advancement. Basically, I'm really trying to be quick. We don't have much time left. Construction staging. This part is very important. Again, when you define the loads, you define the type of loading, like a construction. You can see here, I'm not sure if visible or not. So when you define self-weight or like the barrier, wet concrete, built up pavement, you can define type of the load, dead load. So if they are defined, usually we define as construction staging because we want to see the result in each construction stage and also in the final stage. So if you do that, to make the result, your analysis result meaningful, which is sometimes I have seen people miss that, you have to go to the analysis tab and then create construction stage dead loading. So group all of your loading in one group, like if there is like built up pavements or whatever you think they happen together as a construction stage, you can create one loads, and then in the result, in the load combination, you will see one item. Otherwise, you will have many items to do a load combination. As you can see here again, we are talking about activation of the temporary barriers. So as I said earlier, when you put the plank on the abutment, is simply supported. So first, you have to activate your temporary. You see here in the boundary condition, I have a temporary condition. And after that, I remove it and bring it here in the next stage. This is like stage 3. So when the cast is completed, and then this is very important, you define your edge of the structure carefully here. So this is like you can see here the plank. It means when the planks, prestressed planks comes to the side, it has been already reached to the 28 days of compressive strength or 7 days. So then the design and analysis will be run based on this number. But this duration, which means is different from this age, that means how many days that stage will take. So it means after finishing putting your in place your plank girders, it takes 10 days to finish this stage, to go next stage. So in nutshell, we should basically define elements, boundary, and loads. We have to create groups, and after that, we have to group. We have basically need to define those group, bring those group in construction staging, which comes automatically here, as I said, and then define it. So moving loads basically is another interesting topic. You can have, first you need to define your load. In this job, we were doing M1600, but sometimes if you're using a railway, you have 300 LA, you can simply go and this is available. You just go and choose the type of loading. Sometimes some people use, I have the project work on the MTM, which is Victoria, 245 LA. Simply, you can just use 300 LA like for railroad and then apply with your load factors, like let's say, and then you just have your modified load without creating a new load cases. Very important factors in moving loads, I want to just discuss basically two things. One is concurrent forces and another one definition of lane. So when you have definition of lane, you have two options. Option one is a cross beam, which I usually use that. If you have a grillage model, you have to use cross beam, which means when you have the load here, the software calculates the stiffness of your girders and the slabs together as a composite section and basically considers the diaphragm action and transfers the loads as per stiffness of your grillage model. But if you use a lane elements, the lane elements just you define, and if you have load here, you have to choose one beam and one section to take all the load. If you choose that beam, the load from here directly, everything goes to there, plus the eccentricity. So you use it when you have only one beam, in fact. Like let's say you are designing a super T, and then you just want to say what's the section, you have only one beam, you use a lane element. But you have, usually with grillage models, goes with the cross beam. That is, you have to define this cross beam as your cross section when you define your members earlier in the member definition. The another point is basically concurrent forces. This is also very confusing sometimes if you don't speak. But it's not confusing, it's going to be a reasonable result, because if you don't do concurrent force and reaction, so if you imagine you have a beam 20 meter and then you have bending moment in the center, maximum shear in the support, but if you don't do concurrent, takes the bending from center, maximum, like let's say shear from the support, and design for that. While you don't want to do that, you want to be have optimized design, you just choose concurrent forces, and then you see that. Otherwise, you see all envelope result. Since we don't have much time, I'm trying to skip this part. It's like basically you can convert all of your loads as a result. When you go to the result, finish your analysis, you can get your every single loads and every single beam seeing like convert to the static. So check the result analysis is simple. So you have to check the results. But this part is not simply checking the result. This is converting the moving loads, because moving load usually you can choose like what type of load it's going to be. Like it can be influence line or all points. So you can read it later on. But what I'm going to get at here is sometimes you want to define centrifugal forces or derailment if you have railroads or braking forces. So you don't need to define manually. Basically, this is the most accurate way. You run it, and there is an option to convert moving loads to static loads. And then from there, you can see here, my moving load is already converted to worst scenario static load. And then from there, you can convert it to the centrifugal forces. So that is very handy and very important. So the last two slides are dedicated to design requirements. Probably most of you familiar with the design requirements. When we want to design, usually serviceability is the case for the design, governing check most of the cases. And for ULS, usually do a defined reinforcement rail and then compare result with the hand calculation. So there are the most important things I usually check with Midas results. When you do a Midas result check, and so as I said, every software has its like modeling, analysis, and design phases, right? So I would say it's very handy and is a perfect solution for modeling and analysis. When you go to design, for Australian standard, is still under development. So it's like, that's why some part of that, if you are designing a precast segments, you have every option to design in the PCS. If you're designing a steel structures, it is under development. But then for this, you usually need to go to check these items. If you do a PSC design, precast composite design, basically you go in this section of AS 1500, and then everyone knows that about the requirement of the cracks. So you have like 0.25 of root of F prime C. So the stress should not exceed. If exceed from that level, there are requirement if you have reinforcement. So this is the maximum limit. And in Midas, you can see the result here given. So you can go to PSC and you have to check all of these items one by one. Some of them is for transfer stage, some of them for basically a final stage. But I would say you don't need to check a design for stages. Design should be checked for basically final stages. And unless for the transfer stage, you have to check making sure your stress is not exceeding from the limit. One thing you have to be very careful. So when you come up and take these results, so the code allows you to have some tensile stress, unless some clients say zero tension, then you can't really rely on that. That's the project specific. So if you are able to follow this code, so you have some flexibility. If your reinforcement center to center is not exceeding 200, then the code allows you either you have more stress. You can see here 0.25 goes to 1.5, then the code allows you, if you have a reinforcement, to go to 3.5 tensile force, and provided that your reinforcement stresses stays below this limit, depending on the size of rail. So one thing you have to be very careful is basically negative and positive items in design phase. So Midas gives you a compression negative result for the result which is depending on the analysis, but then it's talking about the ultimate design, which is the design items. The tension is negative. For instance, here you can see here we were checking the transfer states at the bottom. So this is checking the allowable stresses and giving you what is the top. FT is the top fiber tensile force. You can see here tensile, and then here is the compression. So at the bottom, you have basically these forces. It's a bottom pressure, compression. And Midas checked for you. After that, you have to check basically max electrical strength, which is ultimate, shear is ultimate, and then the rest are basically in the SLS check. I think I can say that's one more thing is that I want to add, you have to go and check your design value in the Excel form. It's a must to check all the design values. Sometimes the software misses to give you allowable stress. You have to check manually. Yeah, that's all. And I think we have a few minutes left to pick some question if anyone has a question. Thank you.
Okay, if somebody have a question, you can type it down by clicking the question tab in the GoToWebinar navigator. Arash, can you check it?
Sorry? Yeah,
can you
I
check
can see.
the question?
Yeah, I'm checking that. Yeah, I'm checking that. I'm happy to, you can leave my work email address, and if any question comes across, you can send through email. Since we don't have much time here, I'm happy to answer and through an email sometimes later if we don't have much time here, because I can see it's 1:30 and then also have other meetings today.
Okay, do you have about 10 minutes?
Yeah, if any question, I'm happy for 5 to 10 minutes to stay online, but I'm happy to answer all the questions through an emails. If someone wants to send email, you can leave my work email address and I will be happy to answer.
Yeah. So in the questions bar over here, click the questions tab here and then choose that questions you want to answer, and then you can start answering. Arash, can you see the questions?
I don't see any questions, Adam.
Yeah. The first question is this one. Yeah. What forces seems to be the driving your decision on the construction sequence? Is it the soil pressure? Yeah.
Good question. Not really. It's the construction stage is not only design. Is the soil pressure is just one factor. So soil profile is, if you mean soil profile, it's very important, because in some cases you have, let's say in this structure, if you have a different soil profile along the length of the wall, what will happen? You can't even really run a linear response spectrum analysis for your earthquake, because then you need to go and run a time history analysis. So then having that's huge impact on the fully integral bridge, then it's not worth having a fully integral bridge. Yeah, that soil is very important factors. Yeah, but it's not the only factor. And again, I won't say the most important factor is soil, because you can still accommodate in your structure and the differential settlements, and still you can have your piling designed properly. No, it won't be the first factor to me, at least.
Okay, thank you. It was the question from Zaira. And the next question is from Azri. And the question is, what is the maximum spans could go for fully integral bridge design?
Look, this is not something a written rule. Australian standards, if you work in Victoria, there are guidelines, BTN, I don't know, BTN 11, or they are limiting for steel structure 60 and concrete structure 70 meter, if I'm not mistaken. But again, if you are talking about, we have to understand, when talking about the full or semi-integral bridges, we are talking about even super T, right? Yes, I would go. If full integral bridge, I won't go more than 40 meter. If I 35 to 40 meters myself, because the impact would be huge on your peer, and then I think it's not worth it. But unless you don't have, yeah, I would say 40 meters for me is for integral bridges.
Okay, thanks. And the next question is question by Amiru. He says, can you please elaborate on how you apply the construction load for the abutment back wall, such as earth pressure and etc.?
Okay, so yeah, I was a bit faster in the interest of time. So construction stage, I will explain how to apply it. You can go and basically find the tutorial. So what I understand you said the load application. So first you have to group your loading. So it's like you have to define, it's like what are permanent loads and what are the temporary loads, and seismic, whatever loads you want to have in each stage. In fact, like if I have 4 stages, so those loading which come in the stages, not in the final stage. And for instance, the moving load doesn't need to be in the construction staging. So how I apply that, first you have to apply concurrently with your model here. So basically, back to construction stage. So here is the loading. So first you consider, let's say you have you have bottom to top, right? So if you have bottom to top, I don't know, it's like I can't move my, okay, let's say in this image, bottom to top. First you have soil pressure and water pressure at 2 sides, right? And it's a very important point to say, sometimes when you do a load combination, we don't have to talk about the load combination. You have to create 2 different load combination for construction staging. One is the favorable, one is basically adverse effects. When you have a soil, full integral bridges, you will have basically, you need to create sagging and hugging load cases and then apply the construction stage for each load case. The reason is that because if you have a pressure here, K active, and your K here, that it will be your negative bending moment due to the pressure at 2 sides, at the sagging moment, at hugging moment, at 2 ends, will be reduced because of pressure. So you have to have 0 pressure and you have to have 100% pressure. That's one thing. So the load cases should be divided. This is first thing everyone should note that. Second is like you define your loads. You activate your loads as Ka at stage 1. You can see a stage 1 here. Then you want to remove that, you deactivate the load and activate the load K0. So that is the way you change your load cases in each case. So here is a stage. In each stage you need to define, and the next stage you need to remove. So that is a simple way of explaining that. But I hope that's answered the question.
Okay, thank you. I would like to apologize in advance that we have a time limitation, so I cannot read out all the questions. There are a lot of questions, so we're gonna do 2 more questions, and then those who didn't get the answers, you can privately send the email to Arash.
Sorry, Adam. I have to be very quick. I can take 1 more. I'm sorry because I have already scheduled another meetings.
Okay, this is a question from Jennifer Annett, who is the next speaker of our webinar, and she said, did you ever check the creep effect calculated was correct as your hand calculation?
Come again, please.
Did you ever check creep effect calculated was correct as your hand calculation?
Yes, that's a very good question. Yes, we have checked that, and then I have few things which was not correctly basically correctly defined. And in fact, in my design numbers, what I say is like in my analysis, the creep was good, is correct. But then in my result, I had noticed as I said here in the last points, I was emphasizing on the point that there are some items which is basically need to be hand checked, especially in the design. So my input data was correct in terms of creep, but in terms of the design numbers, I needed to recheck and then basically also raise with the Midas team, and then they basically realized there are some bugs and resolve that. So that's why I was always saying you have to check. But the creep, yes, it was all right.
Okay, thank you. And for those who couldn't get the answers, or who have a further question, you can send an email to Arash for your answer.
Yeah, happy to pick up, happy to answer.
Yeah.
I'm really sorry because we are scheduled from to 1:30 and I have another scheduled meeting at 2.
Yeah.
Yep.
Apologize for the lack of time, and we will come back with the better time planning and the better materials on the next session. Thank you again for everyone to attend the Midas IT Expert Seminar. Thank you.